recording started. A couple of preliminary notes. I got the scores from the shelf exams that you guys took last Friday. Got some of them late last night, got some today. They're all posted. Those scores may be a little confusing to you. What you have to do is take the score that's there for you in Canvas and subtract 25 points. So if you got, if your score, I'll erase this in a second, example, if your score is 85%, you have to pull off 25 points from that. That will give you a 60, and that's your raw score. You may say, well, what does that 60 mean? I will post a percentile scale that shows you, gee, you got a 60, here's the percentile you're in. You got a 45, you got an 80, whatever. I'll put that in Canvas tonight, and I'll post an announcement, just depicting what I've said here. So that's how to figure out your score. But we've just found in pharmacology the easiest thing to do is it's really simple. To add 25 points to a student's score, because 25 percentile is 45, a raw score of 45. We add 25 to that, you're 70, and it's like, that works. When it doesn't work so perfectly is when one of you guys scores an 85. There was even an 88 this year. That's like, an 88, well, I can't add 25 points to that. All I can do is give you 100% for the final. So, but that's the system we use. Okay, for next week, when I'm coming to visit you guys for the final time, what we're going to be doing, there's those 3 modules. There's 3 modules that we'll be working through: the harm, the diagnosis, and the therapy. You guys need to work in groups of 4. Sometimes your TBL group is the best group to work with. When there's 3 modules, and there's usually 6 groups to a class. So what I'm going to do, when class starts, I'm going to say, okay, this group of 4, this group of 4, this group of 4, you're going to get the module on therapy, you're going to get the module on diagnosis, you're going to get the module on harm. And you're going to need to present those. So I'll remind you, as you come up, it works best if somebody gives the introduction, somebody gives the method, somebody gives the results, and somebody gives the conclusion. Then there's the worksheets to go through. But your group, you don't know which module you're going to be called upon to do. And half of you will be in a very secondary role. There'll be 2 groups doing like the therapy module, but really only one group will come up. I may call on the other group. My point is, your group has to be ready to present any one of those 3 modules. So you've got to go through and work through the sheets and read the article carefully and see what your criticisms are of the article or critique it to be ready for next week. That's not clear, let me know. Okay, and I will be posting the percentile scale so you guys can figure out what your percentile score was. No, we are not. I don't know how that 9 in the morning stuff got started. If you look at the statistics syllabus, that tells you when we're starting. It may be a little bit closer to 7, like 6:45. I'm going to try and get there by 6. I don't know. AM, no. No. We are talking in the evening, just like we did for the pharmacology TBLs and exam reviews. It's the exact same thing. I'll let you know whether I'm going to be there right at 6 or it may be more like 6:45.
It's like
but I'll get back to you on that. So, yeah, I don't know how the secretaries at various places picked up on that 9:30 that somehow I put that in a syllabus somewhere, and it's like, we're not doing it. Oof. Tape it, you guys. I'll be taping it. So, who cares about the NCAA championship? And with what, a BC? Yeah, that's what people usually use. that doesn't apply to Evansville. It's just you poor guys at Terre Haute that have that difficulty. So, ha ha ha. Okay, let's get started on this handout, the second handout. We need to talk about these various tests in kind of a brief way that we use for different situations. For example, a lot of you are familiar with the student's t-test. We used to just call it the t-test. And that t-test is used to distinguish between two groups, like a placebo and a treatment group. So, used to see if there's a significant difference between two groups. And it's only used for two groups. If you have three groups, you can't use a t-test, because each time you run a test, there's a 1 in 20 chance of p less than 0.05 when the null hypothesis is true. The null hypothesis is a hypothesis of no effect. So your placebo and treatment, there is no difference between the two. When you run a t-test, there's still a 1 in 20 chance you're going to find the difference. If you go back to what we talked about power last week, you can't say, well, I'm going to make it 0.01, because then you're very likely to be making a type 2 error, where you say there is no difference when there really is one. So, or actually it's a type 1 error. No, type 2. When you go to 0.01, it's a type 2 error. What are you going to do when you've got a test for more than two groups? And that's when we use an analysis of variance. And you'll see that title, analysis of variance, is a very good description of what's going on. Most of us, if you had a formal statistics class, you probably ran through one of these by hand. They're horrendous. And I can remember as a grad student doing this, coming up with an answer, but I didn't really understand what I was doing. And then I ran across this discussion written by a statistician. I thought, oh, this is a great discussion. But we use an analysis of variance when it's multiple group comparisons. More than two groups. So it's just placebo treatment, you use a t-test. When it's several different treatments, you can't use a t-test because you keep multiple t-testing. And each time you do it, there's a chance of 1 in 20 of finding significance when it's not there. So multiple t-testing is no good. You have to use this analysis of variance. And best way I can do it is explain it is to go through this example. We want to test the hypothesis that diet has no effect on the median cardiac output of people living in a small town. The null hypothesis is that there is no difference in heart rate due to diet. So we select 4 groups of 7 people from the town, 200 inhabitants there, kind of like the 200 Martians. But anyhow, we pull these group out, and we've got people that continue eating normally, people that eat spaghetti, people that eat only steak, people that eat only fruit and nuts. And then we look at this the kind of data that we're given. And you're left thinking, well, look at that spaghetti diet. Isn't it a little bit higher? Or is that just due to variability? And that's the question you have to answer. And in this example, this is mean plus standard deviation, so it's actually presented correctly. S all by itself is standard deviation. So that's mean plus or minus the standard deviation. Come back. Good. And keep in mind, standard deviation squared equals variance. That was from probably the first page of the handout last week. keep in mind that standard deviation is not affected by sample size. All right, so, and I'm going to put some numbers on this. Let's say the control diet is 4 plus or minus 1. Spaghetti is 6 plus or minus 0.8. Steak diet, 4 plus or minus 1.4. And finally, the fruits and nuts, 3 plus or minus 1.75. Okay, if I was to ask you guys, you won't get out of medical school until you figure out the average variance in those diets, what would you do? How are you going to figure out the average variance? Don't think hard. PPO, you're close, but you calculated the average standard deviation. I want the average variance. Yes. Yes, big time, that's it. So we'd go with, let's see, 1 squared for the controls, plus 0.8 squared, plus 1.4 squared, plus 1.75 squared, divide that all by 4. And that's one way to figure out our average variance. Note, when you look at it this way, if one of those means is different, let's say the fruits and nuts are way out here. What effect is that going to have on the average variance? We're going to get rid of that one. We're going to say this was, I don't know, 7 plus or minus 1.6. What is that going to do to our average variance? I like Dummy's answer. Not much. Yeah, no, because basically all you're doing is 1.75, we'd scratch that out and be 1.6. So, the point I want to make here is the average variance is not affected if the diet alters cardiac output. Average variance is not changed if the diet changes cardiac output. Because the variance is calculated with respect to the mean of that particular sample. Okay, if you're following this, and I hope you are, look at this last line down here, the means of the samples. So this is going to be mean plus or minus standard error. This is the spread of the means. Something quite a bit different. You go back to our Martians that I talked about, and I said, yeah, you pull out groups of Martians, and you can calculate a mean for that sample. Or what you've done here is you pulled out 4 groups of Martians and looked at their 4 means. Here we're doing the 4 diets. So this is the standard error. It's the spread of means. Now, that's standard error. Let's look at let's bring the fruits and nut guy down here. Will that spread of means be affected if the fruits and nuts were at 7 instead of 3? Yep, it will be. So this is what tends to get lost in actually calculating an ANOVA. Calculating that standard error is not easy. That's fairly involved. You get in, it's a long arithmetic thing. People hardly do it anymore. It's so complicated in a computer. You just hit a button and it's done. But the point I want to make here is standard error is changed if diet alters cardiac output. Okay, let's sort of typed it down here. The question facing the investigator, are the observed differences due to different diets or simply variation, which is always the question, is it a treatment effect or is it variation? Let's see, when the hypothesis that the diet does not affect cardiac output is true, and that's the null hypothesis, the variance of each sample of 7 people, regardless of what they ate, is an equally good estimate of the population variance. So we simply average our 4 estimates of variance within the treatment groups, and that's what we did above. And as I mentioned, the variance within the treatment groups is not affected if one diet does change the cardiac output, since the variance of each sample is computed with respect to the mean of that sample. So a mean that's way off doesn't matter. But now we can estimate population variance from the means of samples, from that last line down there. And we've hypothesized all 4 samples were drawn from a single population, meaning the diet didn't affect their cardiac output. Standard deviation of the means will approximate the standard error of the mean. Now, recall that the standard error is related to the standard deviation by this simple equation. Standard error equals standard deviation divided by the square root of n. Well, we can get the standard error. It's a long calculation, but it can be done. And with a computer, as I said, it's extremely easy. So we get the standard error from those 4 means. We know what our n is. So if we know what our standard deviation, if we know what our standard error is, and we know what, so this is known, this is known. Solve for standard deviation. Once you get that standard deviation, square it, and then you've got variance again. Solve for standard deviation. Then square it to get variance. See, this is a different way of getting variance. And what we're going to do is compare this variance to the variance that we calculated on the previous page. And what's the name of this thing? This test is called the analysis of variance, because that's what you're doing. You're analyzing variance by 2 different means, by 2 different ways, by 2 different methods. I don't want to use the word mean here. So note that this particular variance, it is increased if one of the diets alters cardiac output, because those means will be spread out more. But then we do this analyzing a variance, and we compare the population estimated from the sample means above versus estimated from the average of the sample variances previous page. And if it's 1, if f equals 1, that means it didn't matter whether you calculated variance from the sample means or from averaging the sample variances. On the other hand, what if f is 10? If f is 10, that means that numerator was quite a bit greater. That means the spread of the means was pretty big. So if f is a big number, the variability between the sample means is larger than expected. So we reject the hypothesis that all samples were drawn from the same population. In other words, diet does change cardiac output. We reject the null hypothesis. By the way, that F value, t-test gives you a t value. That F value, you will use a computer. We used to use the stat table. And that'll give you a p-value. Because none of these numbers make any sense from a test until we convert it to a p-value. Once you see, oh, it's 0.03 or it's 0.01, it's like, oh, then we've got something. You might think you're done at this point, and you go back and say, okay, let's say that fruits and nuts was the real outlier there. I'm going to say fruits and nuts is the different group. You don't get to do that. You actually have to run another test to see which group is different. So we call them post hoc tests. So to see which groups differ. We're going to use, there's several of these. The Duncan test, the Bonferroni test, we call them post hoc tests, they're after test. They're follow-up test. But they still have to be done. So, once again, 2 groups, you just use a t-test. More than 2 groups, in this case it was 4 groups, you're going to need to use an ANOVA. And you can't use the t-test for when there's 4 groups because you're running several t-tests between those groups. And each time you do it, there's a chance of 1 in 20 of finding significance when it's not there. If the null hypothesis is true, 1 out of 20 times, you're still going to find p less than 0.05. So you don't get to do multiple t-tests. That's been one of the biggest problems in the literature. The statisticians have corrected. As medicine's become more quantitative, we've stopped a lot of that. But historically, that was a big problem, just running multiple t-tests. Okay. This is about as complicated a discussion as we want to get into about types of regression. They're incredibly useful. You're going to see an interesting example in a couple of pages. But you can get lost with a true mathematician teaching you, and it's like, what is it you need? When we talk about logistic regression, for example, we're using it to determine the odds of a particular outcome. So think of this as an extension of an odds ratio. An odds ratio we looked at last week, and that was when you were studying, you had people that were sick and people that weren't sick, and you studied their exposure to a particular possible pathogen, and looked to see if their exposure rates were different. Logistic regression isn't looking at just at one factor, it's looking at several variables at once. So as I say, it's especially useful and applied to these case control studies. But what you're going to do is, the odds of a disease occurring can be equal to several variables. I was going to say X plus Y plus Z, that particular disease. And let's say X, whatever it is a little bit more important than the other variables. It'll have a coefficient of maybe 3, and the other is maybe a 2. So the coefficients will emphasize which of those is most important. But the point is, look, logistic regression is trying to come up with several things, because quite often disease development isn't just one thing. It's more than one thing. Notice that when we look at logistic regression, it doesn't concern itself with time. A cohort study, where you follow people for 20 years, that looks at time. But this is not concerned with the length of exposure. But it can give you some very interesting results. The odds of oral cancer, your book talks about, the Glazier book talks about, and it talks about having HPV, actually other things like frequency of brushing your teeth, and your dentition, and what's your family history, and are you a smoker? You start adding all those different things in, and it's like, all right, maybe HPV is the most important, but it's not the only thing. Okay, linear regression. Used when the relationship between two variables may be a functional dependence of one on the other. So the example I give is blood pressure and age. And get all this scattered data, and then the computer draws a line through it, something like that. And generally, as we age, our blood pressure goes up. In this type of regression, you might say, well, just give me a correlation coefficient. You've got a lot more there than a correlation coefficient. I can tell you that it's highly correlated, but this slope is going to depict or yield the mathematical relationship between X and Y. In other words, as we age 10 years, how much does our blood pressure go up? That's what the slope is going to tell us. So a linear regression gives you a lot more. That's very useful. Okay, multiple regression is just an extension of linear regression. And in multiple regression, we're looking at several factors, more than one variable. Is used to predict the value of Y. So, now if you're looking at blood pressure is equal to age plus sodium intake plus the person's BMI plus their activity. Several factors come together. And then once again, you can have coefficients in front of each of those. Let's say age is 3 here, but the coefficients will give differing weights to the variables. So age was by far the most important. You might expect that to have the largest coefficient there. So linear regression, multiple regression. Okay. Something else you guys are going to see are these Kaplan-Meier survival analysis, where they graph survival data from a randomized controlled trial or even a cohort study, and this addresses time to an event. How long does it take? And a big point here is no adjustment is made for confounding variables. We'll see how we can adjust for confounding variables. Again, confounding variables are those things that, gee, you realize your two groups weren't the same age, or there's some difference in the drugs they were taking. How can you adjust for that? A Kaplan-Meier curve cannot. And what it looks at, time to an event like failure of an artificial hip. Engineers use it to test light bulbs. We changed a light bulb. And they'll actually use when they come up with a new light bulb, they'll use a Kaplan-Meier analysis curve, survival analysis, to see how long does the light bulb survive and what affected survival. Quite often, the event, it might be an MI, it could be death. The example given here is taken right out of the package insert for simvastatin. So we're looking at simvastatin versus placebo. And what we see, proportion alive on the y-axis, years after randomization, here's our difference between placebo and treatment. And usually these studies are going to stop. You have to stop them when the P is less than 0.05. When you're showing that your treatment is either harmful, causing more people to die, or it's healthy and preventing people from dying, and you've gotten to P less than 0.05, you get to stop. Okay, the next page. This is what's coming at you guys. It's so, I don't like statistics, but I sure like what they can do for us. That's these Cox proportional hazards regressions. It's like, what a name, Cox proportional. Usually people just say it's a Cox regression. But this is an extension of the Kaplan-Meier on the previous page. So it's a survival analysis. Also used when the dependent variable is affected by time. That kind of sounds like Kaplan-Meier. Uses several variables that collectively determine the dependent variable. So this is not a graphical analysis. Kaplan-Meier is graphical. But now we're looking at several variables that collectively determine the dependent variable. And it gives us this hazard ratio. Get rid of that in there. That may be interpreted as a relative risk for relative risk adjusted for multiple compounding variables. Hang with me. The example down below gets interesting, you guys, because it's what we started off with last week when I said, should I be on a statin or not? You guys said, well, if you've got some hypertension, then you should. Well, why should I? Why? Well, because you'll do better. Show me. Well, what is it we have? Because this stuff that down below here is like from 2 or 3 years ago. I can remember, I've been a regular exerciser all my life. Somebody who wasn't saying there is no data to show that regular exercise prolongs life. And that person was right 5 or 10 years ago. They're wrong now. There's an Asian study done of 400,000 people. 400,000 that showed there was a decrease. So it would cut it in half. Things like stroke and MI. So, but yeah, we'll just write this in here. Why? What's your survival? That's where we at. To some time point. And that's going to be several different factors. The drug that was used, was it simvastatin or was it atorvastatin? Maybe if we're looking at cancer, what was the stage of the cancer? And what was the age of the patient? So there you've got survival to a time point, but you're looking at several different factors. Kaplan-Meier was just looking at one factor. So, statins are commonly prescribed for the management of dyslipidemia, cardiovascular disease. Increased fitness is also associated with low mortality. Is recommended as an essential part of health. No information exists about the combined effects of fitness and a statin on all-cause mortality. In other words, if I'm your patient, you guys, I say, well, I don't need a statin. I exercise regularly. I get the 40 to 50 minutes a day, 5 times a week, and that's been shown to cut my mortality from these diseases in half. I might still die of cancer right when I get that. Um, so my question to you guys is, if I'm physically fit, is there any reason to take a statin? Or can I avoid the mortality problems of inactivity? If I want to be a couch potato, just take a statin, don't worry about it. That's what this table's answering here. Let's take a look at this. First of all, I want to look at the very bottom here. Yeah. Thanks, dummy. See all these things down here? They adjusted for age, body mass, beta blockers, calcium blockers, ACE inhibitors, ARBs, aspirin. These are all their adjustments they made. Kaplan-Meier doesn't do adjustments. Now, if you're going to do these kind of adjustments, you need a huge group of people. And look at all these different groups. N equals 1060, 1024, 50. I mean, you're talking, I don't know, 10 or 15,000 patients here, at least 10,000. So you have to have a huge sample to be able to do these adjustments. So you have to have a large N. Okay. Now, the different columns here, deaths, unadjusted hazard ratio. And remember, you can think of a hazard ratio as a relative risk. Age-adjusted HR, what we really care about is the fully adjusted HR. That's can be thought of as a relative risk. And then, of course, on the far right is the p-value. The comparison group that they used was people that are least fit, but they're taking statins. So that's your reference group. And I'm not sure why they chose that as the reference group. You could pick any of these groups as your reference group, really. All right, least fit statins. Well, least fit, no statins. Oh, what happens here? Relative risk of 1.35, meaning you're more at risk of a cardiovascular event if you don't take the statin and you're least fit compared to somebody who's least fit taking a statin. So clearly there's a benefit here. These people see an increase in their risk. Now, those numbers in the parentheses there, the 1.17 to 1.54, that's the 95% confidence interval. And this is, they use standard error here to come up with a 95% confidence interval. Notice how nice that confidence interval is. It tells you it's somewhere between about 1.2 and 1.5. All right, going on ahead here, we look at somebody who's moderately fit and they're on a statin. So about a 35% drop compared to the least fit with no statins. Notice the next group down here, 1.02. Moderately fit, no statins. So somebody can be moderately fit and not on a statin, and then be equal to somebody who's least fit and on a statin. So those two groups are equal. So in other words, exercising equals the effect of a statin. Moderate exercise will equal the effect of a statin. So you guys are going to have patients that can't take statins, and they're going to say, so I'm screwed. You're going to say, no, you're going to exercise, and that's going to equal the effect of a statin. Notice also that on this group, that 95% confidence interval crosses 1. Or it encompasses 1, 0.88 to 1.2. So it encompasses 1.0. Therefore, there's no difference from the treatment group. Or from the reference. Let's say from the reference group. That way to say it. You could say there's a difference. You could say it's 1 point, hold on, it's, it's 0.88, or you could say it's 1.12, and I'd say, but it encompasses 1. When the relative risk encompasses 1, that means, and that's your 95% confidence interval, you can't exclude 1. If you can't exclude 1, you don't have a treatment difference. That's a big point, you guys. I don't have a lot of room to write that there, but when your 95% confidence interval encompasses 1 on a relative risk, what you're saying there is that the null hypothesis, you can't prove it, but our data failed to show that there's a difference. And in this case, our data failed to show that there's a difference between least fit statins and moderate fit no statins. All right. Continuing on, fit statins, fit no statins. Let's see. Look at these last two groups. Highly fit statins versus highly fit no statins. First of all, no statins, look at that. That's approximately a 50% decrease in cardiovascular events just because somebody was very fit. So my question to start off with was, okay, if you're really fit, do you need a statin? Will it still be helpful? And what do we see here? It goes all the way down to 0.3. So when you look at those two groups, a person who's highly fit still benefits from having a statin. You can think of exercise or statin as lowering the relative risk to 0.5, and then adding the other one on, whether it's exercise or a statin, as cutting the risk in half again. So you go from 1 to 0.5 to 0.25. I'm missing you there, dummy. So what that's showing is there's still a benefit of a statin in highly fit patients. But this is what we didn't have. That study was, I think, done in 2014. So patients will ask these questions, you guys. You could say, well, the recommendation is, and it's like, wouldn't it be nice to kind of have some idea where that recommendation came from? Because we do have problems with this. There's problems with studies, the risk calculators that have come out that would say, I think my risk calculator showed me as having over the next 10 years, a 16% chance of something like an MI. But then other people said, hold on, that risk calculator grossly overestimates the risk. So there's always problems. You guys, you'll find this far more interesting if you have some idea where this data came from. All right. I don't know that this copied very well for you guys. Sorry if it did, but let's go through it. When you're presented with data and you're wondering which statistical test to use, that's really what this is about. Yeah, which test do you use? You got to decide what kind of data it is. If it's nominal, it's yes or no, pregnant, not pregnant, HIV positive or HIV negative. So it's one or the other. Nominal means least descriptive. So it's yes, no, basically data. It can also be successes or failures. Successes versus failures. So if you're looking at two surgical techniques and trying to compare them and see which was better, each technique would have some failure rates. You can compare those, but that's nominal data. And to test that x squared there is really just the chi-square. Ordinal data is data that's put on a scale. Things like a pain scale, for example, where you rate things from 1 to 5, or 1 to 10 usually, actually. Put your pain, with 1 the least, 10 the greatest. That's an ordinal scale. And then when it's interval or ratio data, now we're talking about things like blood pressure, age, something that's continuous. So, if you have, I don't know why this says 1 or 2 means, but if you've got 2 means, it's a t-test. Treatment versus control, you use a t-test. If it's an association, we really don't have time to talk about that, but this is a correlation. This Spearman and Pearson can be used depending on what kind of data it came from. Your book talks about it in a little bit more detail. If you want to know more, I'd say go. The book is wonderful, you guys, because it was written by an MD who understood what medical students needed. Let's see, the next one is predicting the value of one variable on the basis of one other variable. So this is X versus Y. That's simple linear regression. When it's on the basis of multiple variables, it's going to be logistic regression if it's nominal data. Were they exposed? Were they not exposed? That kind of thing. Or it's going to be multiple regression. And finally, predicting survival time. If it's based on several variables, it's that Cox regression. So that's a quick overview of when you use these different tests. Obviously, it can get really complicated. But starting here will keep you straight, and there's no need to get more complicated, particularly for our purposes at this point. But you guys will pick up stuff as you go along. But understanding this will help you in a journal club enormously. What does that p-value mean? And you kind of have an internal groan when somebody means it's a 5% chance it's right. It's like, that's not what that means. Okay, some other terms to talk about that you're reading, not Glacier, but the chapters that I gave you. The chapters are optional, but they're very good. They're buried in there in the modules. But there's this crucial term called an intention to treat analysis. And when I first heard of this, being a basic science guy, I thought, you gotta be kidding me, I've never heard of anything like this. But let's say you're doing a breast cancer trial with a novel therapy, and you don't get to use a placebo in a breast cancer trial. We know some therapies work. So you're going to do a new treatment versus an established treatment. And you've assigned the patients to the 2 groups. Now, you're this pharmaceutical firm, you're all excited about this drug, you really do believe it works. But a patient assigned to the new treatment, they die before the study's even started. Are you going to count them in your mortality data? Are you going to say, that they were in the treatment group and they died? My initial thought was, of course not, that's not fair. But in actuality, you have to do that. You have to include that death and mortality data. Otherwise, you're going to affect the balance of sickness between the 2 groups that was established by the randomization. So, somebody dies, tough luck. There's going to be sick people in that other group. Maybe they haven't died, but they may die very soon. So, you don't get to throw people out. Some other terms, simple terms that, gosh, they're useful. Let's take a break before we get into these other terms. Let's for a break. Let's take 10. We'll come back at 7 o'clock.
It's really close to...
This is a bad fail. I'm gonna eat some Chick-fil-A.
Sad. I shouldn't say that. Everyone see how Taylor said but?
Uh-huh.
How dare you, T?
Better than 37. As well as the maybe.
Okay. Picking this back up. I want to look at these terms: relative risk reduction, absolute risk reduction, and number needed to treat. Four crucial terms. Relative risk we've talked about already. It has to be incidence data. It's the incidence of a group exposed to a new treatment versus the incidence of a group exposed to a standard treatment. It can be used in different ways. It can be used in a cohort study. People exposed to smoking, people not exposed to smoking. Excuse me. And then there's relative risk reduction, which is 1 minus relative risk. So the example I give here, if relative risk is 0.52, then relative risk reduction is 0.48. 1 minus 0.52 is 0.48. Therefore, the new treatment decreased risk by 48%. That sounds great, and it can be. But one of the big things we found is that relative risk reduction is often used to make results look really good. And you need to be aware of it. Let's look at two trials here. I got different numbers here. It's all right, we'll deal with these. Disease A. Mortality with these new treatment decreases from 100% to 50%. Disease B, mortality decreased from 2% to 1%. It's different diseases. But note that relative risk reduction is the same for both trials. It's 50%. Therefore, you might think these treatments, are of equal value, but they're not. And therefore, what we need to look at is what's the absolute risk reduction? In other words, what's the control incidence minus the treatment incidence? Well, we have 100% minus 50% equals 50%, which equals 0.5. On the other hand, 2% to 1%, which is going to equal 0.01. All right, so that's our absolute risk reduction. Absolute risk reduction by itself, not all that helpful. But this absolute risk reduction, which is the ARR, is extremely useful because it gets used in our number needed to treat. And the number needed to treat because the denominator uses the absolute risk reduction. So ignore those numbers on the right of the equation for a second here, the 12%, the 24%. This is a different example. Let's go back up to the example I was looking at. If we calculate the number needed to treat for disease A, it's 1 over 0.5. It equals 2, meaning you have to treat 2 people to see an effect, to save a person. On the other hand, the number needed to treat for the second group is 100. So if you're looking at, which treatment works better, relative risk reduction, now that's confusing because it looks the same. On the other hand, number needed to treat. Oh, you gotta treat 100 people to save 1, or are you gonna treat 2 people to save 1? They're not equal treatments. They're not of equal value. The other example I give down here, this is just another example. I threw in numbers of 12%, 24%, and when you do that, the absolute risk reduction is 12%. 24 minus 12 is 12. The number needed to treat is 8.3. So 8.3 patients must be treated to prevent 1 bad outcome. So, your book is an interesting example of a statin. It's a large number of people that need to be treated with a statin to prevent a bad outcome. At least the statins are mostly off of patent now, but when they weren't, it's like, this is a lot of money. So the example with pravastatin in the book. Okay, jumping subjects a little bit here. Diagnostic test. And one of your modules is diagnosis. So this pertains really to that module. When we talk about screening, we'll use terms like sensitivity, specificity, and predictive value. And you've probably seen this in your PATH classes. Suppose a particular diagnostic test yields a result such that a patient is classified as disease positive or negative. Nominal data. A few such tests will correctly classify everybody. For one reason or another, there's some false positives and false negatives. For a particular sample in which each member is tested for a particular disease, we can make the following assessment. What we're going to be doing here is a test result. This is a cheap test. Cheap, easy, non-invasive. And we're going to compare it to a gold standard test. And the gold standard usually is pretty expensive, it's often invasive, etc. So we don't like doing that gold standard test unless we have to. But when we look at it, what we'll see is, all right, there'll be times when the test result from the cheap to easy test is true, says the disease is there, so does the gold standard. But you've also got these false positives, where the screening test, well, we'll call this a screening test, it'll have false positives. It's also going to have false negatives. So we have to evaluate this. And looking at the sensitivity, it's the percentage of diseased person detected by the disease. That's the sensitivity. How sensitive was the test? How often did it pick up the disease? And what that is true positives or true positives plus false negatives, because these are people with the disease that were missed. Obviously, you want to test with a high sensitivity. You want, 99 or 100% sensitivity. On the other hand, excuse me, sensitivity is a fairly, fairly intuitive term. Specificity isn't. Specificity is the percentage of well persons classified as well. So it's true negatives over true negatives plus false positives. These were healthy people that were classified as sick. So, sensitivity and specificity. Some people like these acronyms, SPIN and SNOUT. SPIN, if the test has a high specificity and the patient is classified as sick, it rules in the disease. If it has a high specificity, the patient is classified as sick. So, high specificity means well people are classified as well. If the test has a high specificity and you're classified as sick, you're probably sick. SNOUT, if the test has a high sensitivity and the patient is classified as negative, it rules out the disease. If it's sensitive, if it picks up the disease and yet you didn't pick it up in your patient probably doesn't have the disease. So, as the following graph displays, it's not quite that simple because sometimes, frequently, there's a reciprocal relationship between sensitivity and specificity. This is looking at intraocular pressure, and clearly, if somebody has an intraocular pressure of 40, they've got glaucoma, and they're going to have problems with damage to their optic nerve and so on. But there's this gray area. There are people that have intraocular pressures of 25, 26, and they never develop the signs of glaucoma. And so, if your test is to say everybody above 22 has glaucoma, you're going to have some false positives in there. On the other hand, if you want to say, well, I want my specificity to be 100%, so I'm going to use 27 as the cutoff, you're going to have people losing their eyesight. So just be aware there's this trade-off. Okay. Predictive value of a positive test. So from this, from these tables where we get the true positive, false positive, and so on, we calculate the proportion of positive tests that are truly positive as true positive over true positive plus false positive. Basically, this is what you guys are liable to be asked. When you tell a patient they've got a disease, are you sure, doc? That's the question you may hear back. And you're going to have to ask yourself, what's the positive predictive value of that test? And it's not quite as simple as I put there. Let's look at this next paragraph. This is the problem with a PPV. Quite often we call it just a positive predictive value. Predictive value of a positive test increases with increasing specificity and sensitivity and specificity. Okay, good. Yeah, all right, I understand that. But notice that the prevalence of the disease in the population screened increases. Predictive value goes up. And the converse is true. For example, I'll back up here. If a disease is rare, you may easily wind up in a situation where false positives are greater than true positives. Even though you got good sensitivity and good specificity, that can happen. And if you got more false positives than true positives, you told the person, yeah, sure, this test has a high predictive value. You need to know what the prevalence of the disease is in the people it is being tested in. So let's look at the example I got here, because you'll be asked to do this kind of reasoning on the problems and the problem sets. Let's look at this example. Sensitivity is 99%, specificity is 99%, prevalence is 0.5, and I say the positive predictive value is 33%. Well, where did I get that from? Well, let's think about this. you're going to have to set up a model population. And I'm going to say set up a population of 1,000. If you set up a population of 1,000 and your sensitivity is 99%, and your specificity is 99%, what you're going to, and your prevalence is 0.5%, you're going to find that prevalence is 0.5%, true positives, it's going to be right around 5. Prevalence is 0.5%. This test picks it up 99% of the time. I'm assuming you're getting that. Very, very, most likely you're going to get everybody with a sensitivity that high. But notice your number of false positives. Specificity is only 99%. And that means 1 out of 100. You say they're sick and they're not. So your false positives is going to be 10. So 10 out of 1,000. We're going to be false positives. Well, look at that. Only 5 out of 15 true positives are really positive for the disease. That's 33%. So one of the most useful things you guys can do as clinicians is only test the way to get the prevalence up is don't test everybody. Back in the 80s, some people came out with this idea, the statisticians. Once they got back up in their chairs, they were laughing so hard. But they said, you can't do that. And when the HIV epidemic hit, there were healthcare officials that said, test everybody. And it's like, no, this outcry came, you can't test everybody. It's a rare disease, and you're going to have more false positives than true positives by far. It won't even be close. So the prevalence matters, and one of the best things you can do is, only use the test in people that you suspect have the disease. So you can increase if you only test suspected individuals. Because usually what that prevalence refers to is when the test is run, how often is there a disease there? It's not saying that's the prevalence in the whole population. Little distinction there. That'll come out in your problems, I think. Let's see. We can use the same kind of thinking to a negative predictive value. True negatives over true negatives plus false negatives. In this case, what you're able to hear is, wow, doc, that's a relief. Are you sure? I'm okay. And it's the same kind of thinking. Okay, we'll wind up this evening looking at these likelihood ratios. These are interesting because, as I said with the evidence-based medicine, we don't like just a test. We want that physician's experience. As you guys go through your residency, you get out there practicing for a few years, your experience becomes incredibly invaluable, and that's why, no, your experience won't matter. Let's see, prevalence includes no, it doesn't. Okay, good. Prevalence is just how common the disease is when it's tested. Prevalence in your stat book, in your path book, probably usually means you have to look at the context, but the prevalence is in a population. How prevalent is that disease? But when we're running these diagnostic tests, that's not really the question. It's what's the prevalence? We'll see this with an example here. I don't know if I told you this story, but years ago I had a kidney stone, but it presented not dorsally, but ventrally, right where your appendix is. I went to an ER and resident there said, I don't know if you got appendicitis, Mr. Zimmerman, or if you got a kidney stone. I went, it's appendicitis. An experienced surgeon came down quite a while later. He looked at it for about 5 seconds and goes, kidney stone. That's experience. And he was right. They just knew what to look for. So, and actually when I go see a doctor, that's really what I'm paying for, is I want their experience. So, what they're doing with these likelihood ratios is using pretest probability to help determine a patient's disease state. So, and the likelihood ratio is used. Let's look at an example here. We start with a pretest probability. And that's an estimate by the MD based on the physical exam of the patient history, clinical experience. What's their intuition? If we're talking about appendicitis, how often when somebody comes into my ER and they've got lower abdominal pain, how often does it really turn out to be appendicitis? So that's part of, what's the prevalence of the disease in my particular area. But all those things get put together to give a pretest probability. Keep in mind now that we're going to talk about pretest odds. And odds are not probability. So if this pretest probability was, let's say, 7 in 10, 70% chance of a pretest probability, the pretest odds are 7 to 3. Odds and probability aren't the same thing. We talked about that last week when we talked about the odds ratio. So let's run through the example that I've got here. We need to talk about the likelihood ratio, and it's the accuracy of a test. What the likelihood ratio looks at is how often a positive test occurs in a patient with the disease. Well, what is that, you guys? How often a positive test result occurs in a patient with the disease? That is that's true positives, but how often? How often does how often does the test pick up the disease? Bingo, sensitivity. So that's our sensitivity. We're going to take the sensitivity, and the denominator is a little more confusing. That's how often a positive test result occurs in a patient without the disease. That's 1 minus specificity. By the way, you guys will be calculating likelihood ratios in the module on diagnosis next week. Not complicated, just really useful to have this under your belt and know it. All right, I want to look at this in case where it's an example where we're looking for a pulmonary embolism. And we've got our cheap scan result. And we've also got pulmonary embolism done by an angiogram, which equals our gold standard. We're going to say that that angiogram is so good that when it says it's there, an embolism is there, it is. When there's not an embolism there, or when it shows it's not an embolism, there isn't one there. But let's look at what we got here. And I'm going to focus just on the high probability. You ran the cheapo scan and said, oh, there's a high probability of a pulmonary embolism. Well, what it picked up was 102 patients, the scan results said, had the disease. Well, that's pretty pathetic, you guys. Look at this. There's actually 251. So that's a pretty lousy sensitivity. I picked it up 40% of the time. But still, we can use this. And on the other hand, it said there was 14 patients that had the disease, had the pulmonary embolism, and 630 that did not. So we could divide these. That 18.3 comes from 0.406 divided by 0.022. And, when I look at that test, the sensitivity is so bad, I go, geez, what's the use of that? Well, look at this. A high probability lung scan is 18 times more likely to occur in a patient with as opposed to without a pulmonary embolism. That's valuable information. You've got to interpret these tests. You can't just say, oh, the test said no, or the test said yay. There's an interpretation that's required here. You guys are going to see next week, you can also have a negative likelihood ratio. And in that case, what that's asking is, how often you get a negative result. In a patient with the disease versus how often you get a negative result in a patient without the disease. Well, see, they're both useful. But continuing on with this, say we've got an elderly woman, and you guys do your workup on her, and you're very suspicious of a pulmonary embolism. 70% in your mind. Pretest probability 70%, and the test result is high probability. Well, if it's a high probability, that's going to give us our 18 on the previous page. 70% pretest probability, those are 70 to 30 odds. Well, you multiply 70 over 30 times 18.3, you get 42.7. Post-test odds, it's like, what do you mean? The odds are 43. What does that mean? Well, anytime you see, just a number, you can always put a 1 over it. So the post-test odds are about 43 to 1, 42.7 to 1. To convert that back to probability, that's 42.7 over 42.1, and we come up with a 98% probability of a pulmonary embolism. So this is not such a great test. Remember, the sensitivity is pretty bad, but we did this elderly woman, and we may be able to avoid doing an expensive invasive angiogram. Sometimes the dye hurts the kidneys and all this kind of stuff. Now we're 98% sure she's got pulmonary embolism. So using this kind of calculation between probability and odds and likelihood ratio, it can be clumsy, and I would hate to do it in a busy ER where somebody keeps tapping you on the shoulder saying, hey doc, I need this or I need this. It's like, you need to be in a place where you can think quietly, but these Fagan diagrams are quite nice. Because what we do is we start off with pre-test probability, likelihood ratio, and post-test probability. Let's see, check something here. Yeah, to do this Fagan diagram. On the previous page where we had the negative likelihood ratio, how often does a negative result occur in a patient with the disease? Well, that was fairly frequently. That was 1 minus 0.4, which equals 0.6. How often does a negative result? Then how often does a negative result occur in a patient with the disease, or a patient without the disease? That's going to be 0.98. It almost doesn't happen. And you multiply or you work those out, and it comes out to approximately 0.6. And that's going to equal our negative likelihood ratio. We use that on the next page. All right, so we've got two likelihood, we're gonna start off at 70%. We've got a negative likelihood ratio of 0.6. And we've got a positive likelihood ratio of almost 20. It's up here. I'm not going to draw this very well. I'm going to try, but post-test probability, we're somewhere around, I don't know, 96%. So much easier that was than doing the equation. On the other hand, a negative likelihood ratio, still about 60%. So somebody has a negative test. That didn't really help you out very much. That saying is, negative test is not helpful in diagnosis due to the poor sensitivity. We start off at 70% pretest probability. We did the negative likelihood ratio. We only got to 60%. It's like, ugh. Well, that's what you're stuck with. And if you're very suspicious of a PE, you may have to do something more invasive. Unless it's more invasive. So that's what likelihood ratios are. But notice how they're taking a physician's incredibly invaluable experience and combining it with the exam. It's a very nice example of an integration. So, okay, you guys, we're done. So, I will get the percentile sheets posted on Canvas this evening. You guys have been shooting me a lot of questions about how to interpret the exam. I'm not going to really answer those emails. If I can just go ahead and post, and I'll probably put an announcement up to let people know that it's there, and how to calculate their raw score. So, okay, I will plan on seeing you guys next week. Make sure you do those modules. Okay, take care.
There's like 100